We are super pleased to have Kirill Borusyak presenting today a joint work with Xavier. Is it Jarville or Harville?
It's Xavier Jarvel.
Xavier, okay. My
Mhm.
apologies. And I don't know if it's Jan or Jan Spies. Revisiting event study designs, robust and efficient estimation. Uh, Kirill is an assistant professor at UCL, Department of Economics, and without any further introductions, I will pass it over to you, but we'll note that questions are open at any time. So thanks
Yeah.
very much, Kirill.
Thanks so much, Taylor, for the invitation. Thanks for all of you for being here. I would really appreciate if some of you could turn on your cameras for those of you who could. I see a couple of people, but it makes it more interesting and lively. Thanks. So this is indeed my work with Xavier and Jan, and it's kind of a paper with a strange history. We had a 2017 draft for sitting there for a few years, but now with the help of Jan and with some more work, we posted a new draft. So any comments are very, very welcome at this point while we're revising it and hoping to finish it sometime soon. So in this reading group, it really doesn't need a lot of introduction what different diffs in event studies are, but just to set some stage. So we'll be talking about different diffs with staggered adoption of treatment. So we'll observe a panel in the baseline case. I'll talk at the end about various generalizations. A panel of some units I and periods t. We'll observe some outcomes y. You can see my mouse, right? When I'm pointing out. Yeah, good. And then there will be some binary treatment d, which is one if in this period this unit is treated, and for each unit either there will be some moment which we call event time when it gets treated and stays treated forever, like for unit A it's period 2, or maybe this period of treatment is infinite, which means that the unit is never treated, like this unit d in this example. Okay, and as again all of you surely know, different diffs started with like this 2x2 case with 2 units and 2 periods, with the idea that we want to compare the evolution of outcomes in the recently treated units versus never treated units. And it so happened that those estimators like tau hat here can be obtained in the 2x2 case from the two-way fixed effect regression. So y on the indicators on fixed effects of units and periods, and the dummy of the treatment times this coefficient tau. So that's true in 2x2 cases, and then people generalized it just by extension to arbitrary situations with staggered adoption. And so, conventional practice, it would be fair to say, is based on Euler's estimation of some regressions. Kind of this regression equation here is kind of a summary of everything people typically do here. Of course, there may be variations where you regress the outcome on the two-way fixed effects, and then some leads and lags of the event indicator, right? So positive h here, h we'll call the horizon, the number of periods since the event. So positive h, or non-negative to be more precise, are the lags of treatment, so post-treatment coefficients. The negative h are the leads or the pre-treatment coefficients used to test for parallel trends. And then typically or often some of the very long run estimates are often being together in this single coefficient tau beta plus. As a special case of this, also there are static specifications that are also used where A and B are 0, so you just have the dummy of treatment, just as I showed you before, is meant to summarize treatment effects overall without worrying about zigzag dynamics and so on. So all of this you know very well. So what I want to start with before telling you kind of the summary of the paper is that specifications like this, if you stare at for example, the static specification here, we could do the same for the dynamic ones. You could see a few interesting things. So first, you can see this alpha I plus beta t, which to us looks like how parallel trends are imposed. Because indeed, if the outcome has this kind of separable structure, that means that there are some that the gaps between the outcomes of different units are the same across units over time, right? So that's our take on parallel trends. Of course, there may be some noise around them. We don't expect them to move exactly parallel, only in expectation. Then we see that in this specification, like the static one, only if you are treated, there is some effect. So when DIT is 0, there is nothing else in this regression. And so that we view as kind of an implicit assumption of no anticipation effect. So we call it so that before the treatment happens, there can't be any causal effect of it, which is an assumption. And then finally, by writing the single tau coefficient, it maybe, I'm doing this in the talk, I'm not doing this in the paper, but here I would say that, you're implicitly assuming homogeneous treatment effects. Now, it's not necessarily a bad thing to do, but that's a thing that this specification implicitly does. And the implications is what we'll be talking about. The implications and the remedies, of course. Okay, you've seen 5 papers on the same topic. I'm sure this is familiar. If there are any questions, please interrupt me anytime. Okay. So then what do we do? So we'll do a few things in this paper. We'll first make these assumptions explicit and try to separate assumptions from the goals of estimation, from the target parameters that the researcher may be interested in. We'll then show, kind of building on our old draft, which showed a bunch of problems with conventional regression. Some of them have been studied more since, others have not. But today I'll focus not on the problems themselves, but more on how these problems reflect the mismatch between the regressions we run and the assumptions we make. How it's the conflation of different assumptions and the estimation goal that lead to all of these problems. That's what I'll focus on today. Then, once all of this is understood, I'll show you our proposed remedy. So I'll derive the estimator, the estimator, which is robust and efficient. I'll derive it from these first principles, from starting from the assumption and the goal. And I'll show that in the standard baseline case where treatment effect heterogeneity is not restricted, it has this nice imputation structure, which we think is very intuitive and interesting. I'll quickly, I imagine this is mostly an applied audience, so I'll very quickly go through the consistency, asymptotic normality, all of this, and mention how we do inference, which is kind of novel and we hope is interesting, but any feedback is good. And then I'll talk about various more practical issues, such as how we propose to approach testing, which again is different from how it's been typically done. I'll try to place our paper in the huge new literature on robust estimation of treatment effect in event studies, and briefly discuss extensions, because our imputation approach will really naturally generalize to many designs, which are not just plain vanilla event studies. So that's the plan. Any questions? All right. There has been a huge literature. Yeah, please.
If I can. So if you go to your previous slide, the previous one where you have the traditional two-way fixed effects estimator, do we still do we need to be concerned if it's an imbalanced or balanced panel, or does it matter, or it doesn't?
Matters for what? That's the question, right? So, for example, for our estimators, that will not matter at all. For conventional practice, well, I mean, these problems that I'll be talking about will arise even if it's a balanced. I mean, I don't like the word balanced, actually, because it has 2 meanings. Let's say complete samples, where each unit is observed for all periods, whatever set of periods you have. There is also a set of balancing the panel, which is like balancing it around the event time, which is a very different type of balancing, which is actually something that we're thinking about right now, and how but let's not get ahead of ourselves here. Okay, good. So there is a huge literature, as the fact that you all here surely indicates, and some of them, the literature starting with our old draft, talks about the problems with conventional estimation. Other papers to propose new estimators that I'll relate to later. And then there is a lot of interesting other work that I'll not be touching much on today, like why parallel trend is a good assumption to begin with, or what to do if it's violated, or some randomization-based approaches. Will not be dealing with any of that today, but I'll certainly talk more about other imputation approaches out there in the literature later on. So let's get started with the setting and framework, and then I'll go just basically with the same in the same order as I just told you. So let's make the formal setting. So first of all, the slightly unusual thing about our work here starts with the title of this slide. So we'll be dealing with a fixed sample. You may have seen some papers doing this finite population analysis. That's what we'll be doing as well. So we condition on the sample you have. We don't think about any random sampling from anywhere. You've got the units you have. You're interested in various parameters about that sample. We'll denote by D as before the treatment indicator, which is the same as the dummy for the current period being greater or equal than the event period for this unit I, right? So EI is the event time, or infinity if never treated. And we'll consider, just for notation, two sets, omega 1 and omega 0. Omega 1 are the treated observations. Again, that's a fixed set, right? We condition on the sample, we condition on timing of treatment. That's not random, which I think reflects why we use different dips to begin with. That's precisely when, I mean, there are different meanings of the word random, but they're certainly not randomized, and we're not going to be leveraging on that. Say omega 0 is a set of all untreated observations, which could be both not yet treated or never treated, right? So it's a set of observations, not units. So that's just our little notation. And so we'll say that the researcher is interested in some parameter, which we call tau w, which is a weighted average or sum of the treatment effects, weighted with some weights WIT. These weights can be whatever the researcher really wants. Sometimes the researcher doesn't know what they quite want, but we'll show that that's actually a little problematic. So let's say that they know what they want. So W1 is the vector of the weights, which specify the target estimate. Now, what are tau ITs? Tau ITs are the gaps for treated observations between the observed outcome and the outcome the potential outcome YT0, which is the outcome, unobserved outcome, had the unit been never treated. Okay, so that's the target. And this target really includes lots of potential estimates. The standard ones would be just your sample average student on the treated, right? Just for all observations, treated observations you have, you want the average effects on all of them. Or you may want to do it horizon by horizon, so like one period after treatment, 2 periods after treatment separately, and so on. But also all kinds of other things, difference between subgroups, just specify some W's as positive and others as negative, so that they add up to 1 minus 1 equals 0. You could do it weighted by your the importance of your unit, maybe a regional size or whatever. We also discussed that you may want, when you're looking at horizons, in your sample, different horizons come in with different subsets of units where they're observed. So you can kind of balance them out to estimate the effects, 0, 1, 2, 3, and so on periods after treatment for the same subgroup of units where they're all available. Any of this can be formalized with some WITs. Now, of course, to identify things, we need assumptions. So the main assumption is parallel trends, which we make and maintain. So as I kind of alluded to before, the assumption is that the untreated potential outcome for all units has this separable structure with unit fixed effect, time fixed effects, and epsilon, which is noise, which is mean 0. And again, we'll take the fixed effects as non-stochastic. So we'll condition on them as well. Epsilon is the only source of the noise in our framework. This is a slightly unusual, if you've seen some other papers, way of writing parallel trends, but it's equivalent to those. You can just rewrite it as the change over time in the expectation of the outcome being the same for all units. Okay, any questions?
Kirill, in Scott Cunningham, in Scott's write-up, he just has a kind of a question that I think some other people might have as well. This is written at the individual level, but it can be rewritten at like a specific group level that anyone has in mind, right? Is that also the case?
I mean, if it holds at the individual level, of course, you can aggregate. I think that's a better way. Nothing here prevents epsilons to be correlated within across some units so far. We haven't made any assumption like that. This certainly works better for unbalanced or for incomplete samples, where if group composition changes over time, then you don't want to assume parallel trends at the group level. You want to assume it at the individual level. Yeah, it's a it's a different assumption in those cases, which I think is more sensible in many cases. Now, the fact that it's just the simple two-way fixed effect structure doesn't really matter. I'll be talking about that just for simplicity and convenience. But all the results in the paper work with this more general structure where there are some parameters lambda I multiplied by some okay, so let me not give you the general case, just give examples like unit specific trends. You can have in the A the trend T, and then there are unit specific coefficients in it, so that's fine. You can have just simple time varying controls, that's fine. So any of this is fair game, as long as you kind of observe. We don't allow for factor models where you interact on unknown unit fixed effects with an unknown time effect. So that's not allowed. But things like unit specific trends are perfectly fine. All right, so that's the first assumption. Now, this was an assumption on y zeros. For the assumption to be useful, we need to observe y zeros sometime. So the second assumption is no anticipation, and that's that the observed outcome is the y zero for untreated observations. It's kind of a trivial assumption for never treated observations. It's a not trivial assumption for not yet treated observations, which says that future treatment doesn't have effect backwards in time. And that's natural to relax if you think there could be anticipation effects, for 2 periods before treatment. Well, then redefine your treatment as 2 periods early, and you're good. Okay. Then finally, and that's something you would not have seen in other papers, we'll allow for an optional assumption A3, which is a treatment effect model. So what is that? So if you have some economic knowledge that some treatment effects are the same or related to each other in some way, then you can specify that in our framework. So there are some restrictions on treatment effects such that B times tau is 0 for some metrics, for some known metrics B. Equivalently, and perhaps slightly more convenient, we'll write it not as restrictions, but as a model. So we'll say that the researcher knows that tau can be specified as a linear function of some parameter theta, probably lower dimensional, as gamma times theta for known gamma. For example, if theta is a vector of horizon-specific effects, and for a fact, based on some economic theory or whatever, that the only variation in treatment effects that could be there is across horizons, but not within, then you will specify this low dimensional model. But this is not to be confused with thinking that there is heterogeneity and imposing some restrictions. So this is A3 is only made if you have ex ante reasons to do so. Otherwise, it's perfectly fine to have tau equal theta, so gamma to be a trivial identity matrix, and there is no model imposed. That's in fact our baseline case.
I just have a quick question about this, if it's all right. Given that so much of empirical work and application seem to be motivated by a priori theory being unclear or the effect being ambiguous, do you feel like this A3 is a little more useful for things like suggestive evidence, which does seem to have some kind of theory background of okay, we should expect to see a particular sign on these kind of effects? Do you think that's... So
inequality restrictions are not allowed here. Actually, we haven't thought about them. It's only equality. In practice, we don't think you often want to impose this assumption. but we want to allow it to contrast imposing the assumption for a good reason from imposing for a bad reason. And in principle, there are cases where this, could be plausible. So that's fine too. Yeah. Any other questions? Cool. So as a result, there is kind of a true model for the observed outcome that all of these assumptions together imply, which is, two-way fixed effects plus heterogeneous treatment effects times treatment, right? They only apply to treated observations, plus the residual where the vector of taus may have certain restrictions on it. Okay, so I should probably speed up a little bit, or we'll never get through the results. So I'll really go quickly through the conventional practice. I assume you've seen it in our earlier draft or in other papers. So there are 3 problems that we originally discussed in the 2017 paper. So I'll just briefly go through them. So the first one is that the fully dynamic specification, which is an Euler's regression, which includes all leads and lags of treatment observed in the data, is not identified when there are no never treated units. And the reason why it's not identified is that if you're looking for this path of tau h coefficients on leads and lags, then you can add a linear trend to this path, like this, for example, rotating it around -1, which is often normalized to 0. And any rotations like this fit the data equally well. The intuition, I'll skip the details, is that it's impossible in these models to separately identify the trend in the data from a combination of like a linear trend in the treatment effects, treatment plus anticipation effects plus individual effects. So I'll skip that if you don't mind to focus on more interesting things. What I want to say though is that, oh yeah, there is a question. You should just unmute yourself, please.
Yeah, hi. I had a very quick question, which is, so in some of these regression specifications, when people use, continuous treatment, when you don't have like a level like these, when you have a treatment intensity, so to speak, and there is no control, but you're kind of implicitly doing this above median, below median comparison. And if you do a like an event study graph, then so you're suggesting that the pre-trends are not identified in that scenario. If your treatment intensity goes from, let's say, 10% to 90%, and you're using that dose as a treatment in a definitive design.
So I'm not exactly sure what setting you have in mind, because there may be, is it that within the same unit treatment changes over time, or is it that, there is a kind of time invariant treatment intensity and then it's just interacted with?
No, I'm thinking like, just think of the minimum wage literature.
I'd like to defer all of these questions which are not about binary treatments and which are about extensions to the end. I'd like to cover the baseline case, and then we can talk how, about how, what issues arise outside and which of our solutions apply, if that's okay. All right. So the problem with, why this under-identification arises kind of deeply and conceptually, we think, is that the researcher, while writing this regression, is doing a kind of strange thing. They're not really imposing one of the key assumptions of the analysis, which is no anticipation. They're allowing for all kinds of leads to allow for all kinds of anticipation effects. And they don't do it because they think there are anticipation effects. I mean, presumably they only run different diffs because hopefully parallel trends hold and there is no anticipation. They do it for testing, but nevertheless, the regression you estimate doesn't impose this assumption. And by, if you don't impose the assumption you need, well, it can be so bad as not identified at all. You could, of course, in the old draft, we actually even said, oh, you could drop a couple of leads and then it is technically identified. But we think that's bad practice now. Because when you do a particular design, like an event study or different diff, that design comes with its assumptions. You need to be clear about them and understand them and impose them. That's what identifies your coefficients. So this under-identification problem is just really an extreme version of not imposing the assumptions which are needed. I'm not saying one shouldn't test the assumptions. I'll get to that and talk about that for sure. But you should only do this to begin with, do different ifs and event studies, if you think there is a hope, there is a reason that it holds. And then you identify the effects while imposing it. Okay? It's kind of a conceptual point here. Now, the second problem I should really go fast on, because that's been studied a lot since we in the Chose-Martin's paper first pointed out that if you run a static specification with just one dummy of treatments, then the estimand of this specification is some weighted sum of treatment effects. The sum of weights equals to 1, but some of the weights can be negative, and so you can get coefficients which are outside the set of all treatment effects that are possibly there, and so on. So something which you really don't want, like in this simple example with 2 units A and B observed in 3 periods, one treated in period 2, the other treated in period 3, so both are treated. Again, these problems mostly arise with no or few never treated units. Then in this case, the OLS estimand tau will be a short run effect on the early treated unit A in period T, plus half of the short run effect on the late treated unit B, and minus a half on the long run effect of the only unit where the long run effect is observed, the early treated unit A. And that's a general phenomenon that OLS with static specification puts negative weights on the long run effects, which is something which is not really desirable. Now, again, a more interesting conceptual thing for me here is to think why that happens. And this happens, in our view, because the static specification conflates two things. It thinks that it, wants to get some average of heterogeneous treatment effects, some kind of target. Instead, it imposes a model of treatment effect, right? The model, which is in this case super, strict, that all treatment effects are the same tau. And while in some cases we have intuitions that kind of doesn't matter, if you just impose it, you'll get some average. It's not the case in models with two-way fixed effects, or in fact, in any models with continuous controls, that's not the case either. Mechanically, when you impose this model, what you allow OLS to do is what we call forbidden comparisons, which is to use, for example, in the example here, to use the difference between, for example, the evolution of the outcome for unit A between periods 2 and 3 as a reference for the evolution in the same periods for unit B, which was just treated, right? Because for A, the treatment dynamic doesn't change here. And so under the assumption of constant effects that static regression imposes, that's fair game, but not otherwise. And so these forbidden comparisons are allowed. They will be used by OLS because they give you efficiency if the assumption of homogeneity holds, but it creates this problem otherwise. And that highlights that sometimes you may want to do the static regression, and that's when you really believe in the treatment effect model. You really mean to impose A3, but not otherwise. Okay. And then finally, a related issue is what I call spurious identification of long-run effects. So, for example, I'll just give you an example, same one as before. So in this case, if you just impose our standard assumptions, parallel trends, and no anticipation without, with unrestricted heterogeneity, then the long-run effect is not identified. Well, simply because there is no, for different diff comparisons, there is no unit at period 3 which could be used as a reference group, right? Everybody is treated by them. And yet, dynamic OLS specifications, except the fully dynamic one, which is not point identified, but those which are, will give you some coefficient. And this coefficient will be estimated purely by extrapolation of weird sorts, right? You're getting a number, well, you shouldn't be getting a number under the assumptions of the model. So that's not good. So why conceptually does that happen? Same story, right? You're imposing a treatment effect model. Under that model, you can identify the long run effect because it's equal to the short run effect. But without this assumption, you can't, and NOLS doesn't know about that. All right. No questions? Great. So then let's, now that we've seen how OLS screws things up in various ways by conflating different assumptions, let's see how we don't conflate them and how we get something which is robust to heterogeneity and in fact efficient in some sense. So we'll take our main two assumptions, we'll allow an optional A3 as before, and now we'll make an extra assumption, which is pretty restrictive. It's homoscedasticity of residuals, saying that the epsilons are, have the same variance, and they are uncorrelated across, across units and within units over time. Very strong assumption. The efficiency result will depend on it. Robustness will not, so don't worry. So then we have two theorems, really. The first one says that, among all linear, it's kind of the analog of the Gauss-Markov theorem that we know from undergrad metrics, that among all linear unbiased estimators of the estimand of interest, now defined as a particular weighted average of heterogeneous effects, the efficient estimand tau star, tau hat star, can be obtained in three steps. First, you estimate the thetas, the parameters governing the treatment effects, right? Because this allows for restrictions on them, right? How do you do that? Well, you kind of run the true model and just do it, right? The true model being, your fixed effects, and then treatment times the tau modeled as gamma times theta. For example, if you assumed a particular, that all treatment effects are the same and you believe in it for real, then you would just, put that would be just the static regression. But any restrictions are fine here. From theta, you would go in step 2 to the tau. So you would estimate the treatment effects for each observation, just according to the model. And then you would estimate your target by taking up an appropriate weighted average. So this result is almost obvious that, if this is a true model, then we know how to estimate a true linear model under homoscedasticity, well, OLS. The only trick is that our parameter of interest is not theta, is a weighted average of the taus, which are themselves modeled according to theta, but that's fine. Still, the same procedure gives you the most efficient estimate. Okay. Now this, so far, this is not very practical. For example, if you think about our baseline case of no restrictions on heterogeneity, this would really be tau IT here, right? So you would have to run a regression in which each treated observation has its own coefficient. Well, that's a lot of coefficients to estimate, and how can any good come out of that?
This looks a lot like Chamberlain's more general minimum distance estimator for panel data. Is there a mapping?
How so?
Well, he sets it up as essentially a series of individual equations from which he gets reduced form parameters. And then he estimates the overall parameters as an optimally weighted set of minimizing the distance between the parameters using optimal weights.
Yeah.
This is his 1980 paper.
Yeah. No, I know the minimum distance methods. Maybe not quite the exact paper. So I think the setting is quite different. It's an interesting connection, and I'll think about it. I think the setting is different because.
Well, you don't need to go into it now, but
yeah.
I just wanted to see.
Thanks. Yeah. Yeah. All right, then I'll continue. but then we can talk later, and I'll definitely think about it. All right, so as I told you, it's not very practical in the case where the restrictions on treatment effect heterogeneity are not very strong, or there are no restrictions at all, which is the most interesting case. So it turns out that when there are no restrictions on heterogeneity, so the gamma is just, identity metric, so each theta corresponds to, each tau it is its own theta it. There is a very nice way of obtaining this efficient estimator. That's what I call imputation. So that again proceeds in 3 steps, now very intuitive, we hope. So first, remember we specified a model under which yt of 0 is alpha I plus beta t plus epsilon, and yt of 0 is observed for non-treated observations. Well, go and estimate alpha it and beta t from that regression, just on the fixed effects, on the non-treated observations only. Okay. Second step, extrapolate these estimated alphas and betas. So for each treated observation now, impute its potential untreated outcome as alpha I hat plus beta t hat, plus 0, which is the expected residue, of course. And then once we imputed the potential untreated outcome, we can of course get an estimate of the treatment effect for this observation, for this unit in this period, as the gap between the observed outcome and the imputed potential outcome, tau hat it. Of course, there is no hope of estimating this consistently, but that's okay, because in step 3, we'll take the average corresponding to your object of interest, and hopefully it's an average of sufficiently many observations. Otherwise, again, there is no hope. And so the claim is that that's not only giving you an unbiased estimator of your estimand of interest, but also the most efficient one, as long as, in a sense, because the first step is the efficient estimation of the potential outcomes in the untreated sample. So that's the result we show. And that's kind of the main result of the paper. I see a couple of hands, so please, I think Eduard was first. I can't hear you. Then maybe Jake?
Yeah, so looking at this, I get thoughts of the imputation structure of ATHE's 2018, well, now 2021 matrix completion paper, where we're directly trying to find the unobserved potential outcomes. How does the objective here differ simply in that we're willing to directly assume parallel trends, so we take a different approach, or would you say these because we're not trying to use more flexible functional forms here or regularization or anything here? Is it really just different assumptions drive these the differences?
Absolutely. Okay. So it's the model, the parallel trend model gives you more structure here. But we like this quote, which we have in the paper, and I think Scott borrowed for his write-up as well, that Imbens and Rubin wrote in 2015, that every, I can't of course give you the precise quote, but basically causal estimation is always a problem of imputing potential outcomes. So it's always an imputation strategy, but it can be more or less explicit. And so this makes it very, very explicit, which we think is great for reasons that I'll list formally soon, but basically because it maps very transparently from assumptions into the estimator, and doesn't conflate assumptions with each other, with the target, and so on. And so continues to be robust, while also being efficient under homoscedasticity. Any other questions?
Yes. Mm-hmm. How is this approach different from Gardner's two-way approach?
Great. So let me, you both anticipated what comes next on this slide, so let me just do it. So I already said it's efficient. In fact, it's finite sample efficient, just pointing out. So indeed, for the estimands which Gardner and also this very nice paper in Political Science, both contemporaneous with ours, for specific estimands they compare, that's equivalent or almost equivalent Gardner does this second stage regression, which may change things a little bit, but basically it's the same. The difference is that they just, propose, both of them just propose this strategy as kind of a, just propose it, kind of intuitive. Well, we derived it from first principles and show a bunch of properties of it. I've shown you the first one, which is efficiency under homoscedasticity. I'll show you a couple more good properties of this. But yes, we're not the first ones to come up with the idea of imputation. Metrics completion literature did, something similar. And for factor models, there was a paper by Xu in Political Science again in 2017 that proposed it in a different context. So indeed, that kind of relates to science, not a big literature, but a literature on imputation-based methods. We contribute by actually deriving it as as a special case of the most efficient estimator, while we still have the general case as well. Okay, now let me give you a couple of more results about imputation, which for us were quite surprising, both of them. So first, you can actually do imputation. You can characterize, the efficient estimator as an imputation estimator, even if there are restrictions on treatment effects. So I'll not show you the details, but the idea is that if you impose restrictions, for example, that certain treatment effects are equal to each other, that allows you to consider a different estimand from your estimand, which would be equivalent when the restriction holds. Like, for example, the one that OLS does, as I showed you in the example, like short run plus half short run minus half long run, it's equivalent under the strong restriction of homogeneous treatment effects. And so what you can do, if you say that you believe in the assumption, about treatment effect, about some restrictions on treatment effects, then you first modify your estimand to an equivalent one under this assumption, and then just do imputation according to the 3 steps listed here. And that will give you the efficient estimator, just in the same way as this complicated regression would otherwise. So in a sense, even with restriction of treatment effects, imputation strategy is still the most efficient one, just for a modified estimand, which accounts for the fact that certain things are equal to each other, and maybe there is a better combination of treatment effects that you can estimate more efficiently while it's the same under your assumption. That's one result on imputation. And the second result on imputation, which goes back to this quote from Imbens and Rubin that I just gave you, is that in fact, if you take any unbiased estimator of the estimand, now you can think of your favorite of the alternative estimators that I'll briefly talk about later, all of these San and Abraham and Connolly, Santana and Schuzmartin, Hatfui. So all of them are unbiased. So then we show that any unbiased estimator can be represented in this way with these 3 steps, except that the estimation of alpha I and beta t in the estimation step is not the efficient one under homoscedasticity. It's some other estimates of alpha I and beta t that you use in exactly the same way to extrapolate, to get the taus individual, and then to average them. And so then you can think of the difference across estimators as just differences in how, across robust estimators, of course, it's just differences in how they impute alpha I and beta t from the untreated sample. We impute it in the most natural way of regressing the outcome on the 2-way fixed effects, and they would, and that's efficient under homoscedasticity. They would do it differently. Okay. More questions here. Great. So that's really the key step. So let me quickly talk about asymptotics and then get to the practical issues. So for asymptotics, we'll derive the variance and results about consistency and all of that, and most importantly, standard errors. Without the assumption of homoscedasticity, that would be pretty bad in practice. So replace A4 with assumption A5, which is that there is just some clustering of standard errors, for example, by units, but it can be by anything else. That's fine. By some groups of units, that's allowed in theory and also in the Stata command. In fact, we'll do it not just for our imputation estimator, but also for any weighted estimator, really. So we think that it should give you analytical standard errors for the alternative robust estimators, which haven't been derived, but we didn't actually verify this in practice and simulations and so on. So consistency asymptotic normality is really just a question of regularity conditions. So I'll skip those. Of course, if you take some weighted sum of outcomes, you want the weights to be small and converging to zeros, and the Herfindahl index of them should be small and so on. So I'll skip that. The more interesting part is how to get the standard errors, right? So how to estimate the variance. And so that I'll actually talk about for a minute in the most interesting case where, for the imputation case, so with unrestricted treatment effect heterogeneity. So again, remember we have this model with two fixed effects and heterogeneous tau ITs. So we want to estimate the variance of our estimator, of some estimator with some weights V instead of the optimal weights, whatever. So under the clustering structure, that's the sum across units. Oh, I mean, the standard kind of, variance of, the variance of the weighted sum gives you the sum across units of these squared expectations of squared sums of weight times the residual, because the alphas and the betas cancel out. Those are, absorbed in our first step of estimating them. So that's the object we're interested to estimate, right? Like with the usual clustering. And the standard approach would be, well, in our estimation step, where we get the alphas and the betas, we can get the epsilons, right? Just as a residual, as the residuals from this regression. So just use the plug-in estimator. So it turns out that has two problems here. One problem is very familiar, which is that in short panels, which is the standard case people consider, and we do as well, the fixed effects of units are not consistently estimated, and so the residuals are not consistent either. That's problem one. Problem two is specific to the setting here, which is that the imputation procedure sets the treatment effect for a treated observation as the gap between the outcome and the imputed y0, and so the residual is 0, right? It fits treated observations perfectly. It overfits in a sense. So the epsilon hats for the treated observations are zeros, and of course they are not consistent for the actual variance of the epsilons. And so the first problem, again, as standard, turns out to not be a problem at all. Stock and Watson have shown in a similar setting that if you do cluster standard errors, then it's okay that alpha i's are not consistently estimated. But the second problem is where we innovate. And so here's what we do. We say, okay, so we can't separate the error, the residual from the treatment effect for each given treated observation. So instead, we'll not take the epsilon halves, we'll take the epsilon tildes. What are those? So for a treated observation, we'll take the gap of the outcome minus the imputed alpha I beta t. And then instead of subtracting also their individual treatment effect, which overfits, we subtract this tau bar hat, which is some average across many observations of the estimated effects. And by averaging, we subtract the taus and keep the epsilon IT. And so we show that as long as this average tau bar hat IT converges somewhere for each IT, formal conditions in the paper, then the resulting estimator, which is just a plug-in estimator at this point with epsilon tildes replacing epsilon hats, will be conservative in general and asymptotically exact if there is no heterogeneity within those groups that you averaged by. So if tau is equal to tau bars, then this standard error will be exact. If there is heterogeneity of taus among those which we averaged, then it will be conservative, so still valid. And so what you want to do in practice is to find groups of observations which are sufficiently large to remove this overfitting problem. So you can't just take an average of 2 observations next to each other, but also sufficiently small and homogeneous that you're not creating an overly conservative standard error estimate. Our baseline case here is averaging the taus by each cohort and period. So for example, taking the average estimated tau for all units treated in period 5, observed in the period when they observed, right? And so by taking the residual this way with average taus and not your own tau, then you get these conservative estimates, which are exact if indeed there is no heterogeneity within those cells. But if you only got 5 units treated at the same time, then you have to do something more. You have to go bigger and average those taus more to prevent overfitting and prevent too small standard errors, so that the condition that tau hat bars converge holds, and so you get conservative standard errors. These options are in the command we provide. The baseline case should work often, but you need to kind of be mindful of this issue. Any questions here? All right. I hope this was somewhat clear. Now let's get to practical issues. So first, about testing for parallel trends. So as I said, we think that different diffs and event studies should be only used when there is some reason why parallel trends hold. Yet, of course, they need to be tested, and that's very important for praxis. And so if we think of these two assumptions that we want to test, parallel trends and no anticipation, right? That's really what underlies different, these designs. Then there are two approaches proposed in the literature. So the kind of conventional approach is to run your dynamic OLS specification and take the coefficient on the leads on future treatment and hope that they're 0. The second approach, which has been proposed, by the by the papers which developed the recent robust estimators, is placebo. So you say, okay, let's imagine now that treatment didn't happen today; it happened 5 periods early. 5 periods earlier for every unit. Do we see the effects at 0, 1, 2, 3, or 4 periods after this placebo treatment, which is really before the actual treatment? And we hope that there isn't. Is that clear? Okay. So the approach with leads on OLS coefficients is really problematic, as has been shown by San and Abraham's paper, because the estimates on the leads are actually contaminated by the heterogeneity of treatment effects post-treatment. And so you can have a perfectly correct design, A1 and A2 hold, and yet, because of treatment effect heterogeneity, you will reject these coefficients would actually be significantly different from 0. For example, the example of the usage of our commands that I posted on GitHub shows exactly that. Placebo tests are, of course, not doing that. They, by using robust estimators to estimate these placebo effects, they're only using the observations pre-treatment. And that's, by the way, the main conclusion from the first problem, right? You need to, when testing for pre-trends, you really need to only use pre-treatment observations and not post-treatment as well. So placebo tests don't have this problem, but they have a different, more subtle one, which is that they do, for testing, they use their estimator, which is intended to estimate the causal effects. And those things are different things. They're different conceptually. That there is no, robust estimators require you to specify a particular target estimand, like an equally weighted average of all effects 4 periods before treatment, right? That would be kind of the estimand which the placebo test would try to estimate. But that's pointless, right? You don't care what weighted average you are getting if the assumption you're testing is they're all 0. If they're all 0, and then you have a reason to believe in this to begin with, then you just want the most efficient test, the most powerful test, to check that this is indeed the case and not violated on the data. You don't need to think hard about which weights to put on different pre-treatment observations, because the causal effects under the assumption should all be 0 there, just a matter of testing that. And so by imposing that extra thinking, you're losing power. So what we propose to do instead is to just do a very simple parallel trend, pre-trend test, which is to take only the pre-treatment observations, but then here use OLS as exactly the most efficient thing to do. So regress in the pre-treatment sample, or never treated, of course, as well, the outcome on the fixed effects, whatever controls you have, and then some controls W, which are kind of the directions in which violation of the assumption are the ones you worry about. Typically, people worry about some anticipation effects, like, there may be pre-trends like 1 or 2 periods before, something like this. Well, then throw in dummies of like being exactly 1 and 2 periods before, and check that the estimates are not significantly different from 0. But in principle, if in your setting you're worried about something else, maybe you're worried that there is some structural change before and after the crisis, and so the model with just separable fixed effects is not a good model, well, then throw in that and test against, in the pre-treatment sample, test your parametric model with separable fixed effects against the richer model in which a structural break around the financial crisis is allowed. No point in using robust estimation at this point. OLS is just as good, and think about what to throw in. The baseline of 1, 2, 3 periods before is kind of what we think as the baseline and what we implemented with our command. So the reference group here would be like observations prior to, say, -3 periods before treatment, where you think those deviations are less likely or less worrisome. Okay. Any questions?
Kirill, should we also be thinking about the same kinds of problems that like Roth and Ramachan are talking about in their paper here as well? Like, presumably we can still use your estimator with their methods because they can kind of take anything. But is that still a problem here because you're talking about potentially increasing the power? I mean, is that still a problem?
So I think, let me know if I didn't understand the subtleties of your question, but I think our philosophy is quite different from that of Ramachan and Roth. Ramachan and Roth say, well, really, who believes in parallel trends? Nobody believes in parallel trends, and you shouldn't be imposing them. You should do this set identification with weaker assumptions. And then here's a weaker assumption which they developed, that non-parallel trends are at most something. Okay. Yeah. If that's the assumption you truly believe going in, great. This is not incorporated in our framework because we don't do set identification, but of course it could be something this could be done. We're saying, well, but many people do event studies in different diffs. We hope they have some reason to do it, rather than they've been doing it all along just because everybody does. They have reasons to do it, then they should impose it for estimation and test most efficiently. That's what we propose here.
Right.
So if you are in the world where you don't really believe in your parallel trends, and yet, not saying you shouldn't be testing it, but don't even believe it going in, and yet you're using different diffs, I guess their approach is more honest, for sure, as the title of the paper suggests. Yeah.
Yeah. So I guess I was thinking more about the beware pre-trends testing, which is, I guess, just Roth's paper.
That's coming. That's coming.
Oh, sorry about that.
That's coming. Okay, so that's our approach to testing. Now, exactly as Taylor was asking, it turns out, when we actually, just as I know I'm running out of time, but I'll still not hurry up. When we first proposed that, John Roth, indeed, who has this nice 2018 paper, was not maybe whatever. So basically, his paper says that OLS has this problem that imposing, when you condition on the parallel trend test passing, you then you're biasing at least the inference on your coefficients afterwards, because with OLS, the pre-trend coefficient and the causal effects are correlated with each other. Intuitively, I would say they use the same period, 1 period before, the same observations 1 period before treatment as reference group for both. And so that creates correlation between them. If you condition on the pre-trend coefficients being small, you are getting the variance of the post coefficients incorrectly. To our surprise, it turns out that our solution, our method, actually solves this problem. This wasn't obvious to us, but once we checked, it turns out that indeed. So here is the result that we have. That if you test based on the pre-treatment sample only, as I was just advocating just before, then these pre-trend coefficients are orthogonal to our efficient estimator under homoscedasticity. This result requires homoscedasticity, but the fact that they are orthogonal means that conditioning on the pre-trend test passing, whatever pre-trend test, visual, formal, whatever, does not distort asymptotic inference on the coefficients post. So the key things here is that you don't use post-treatment observations for testing, as you shouldn't, and that you're using an efficient estimator. So that's the result. That's an extra benefit of the imputation, or generally our efficient estimator. Okay. Great. So I've been already talking a bit about comparison to other estimators. I'll do just a little more. So at least 3 very nice papers proposed other estimators also robust to treatment effect heterogeneity. I see something in the chat happening. Well, I'll check later. So they all kind of proceed in a different way and in a similar way to each other. So they start with estimating these cats. Cats are not just your nice pets. They are average treatment effects by cohort and period. So for all units treated in period 5, observed in period 7 or something like that. And then those can be averaged. So that's how they proceed. And so what I have, those are robust to heterogeneity, which is great. Now, I already mentioned that as unbiased robust estimators, they can be viewed as imputation estimators with imputation which is not efficient under homoscedasticity. Then we think, oh, fine, but homoscedasticity is not our case in the data anyway, so maybe they're efficient under something else. And of course, depends on the data generating process. But the main difference, which tells us that typically probably not, is that for to estimate the cut for cohort E, so for units treated in period E, they only use period E-1 as a reference. They don't use earlier periods. Those are used for testing in their case. And so even if you start with parallel trends imposed on all not yet treated units, you don't use that for estimation with any of the 3 methods that are cited here. Martens, Simon Abrahams, and Calway Santana's. And in fact, it doesn't, you may think, well, if you use less data for estimation, then maybe you're more robust to some violations of treatment effect of parallel trends. We have a more detailed discussion of this in the paper, but my basic answer is not really. I'll just give you an illustration here where the efficiency game kind of comes from with our imputation estimator. So I have 3 now units here observed in 3 periods, treated in period 2, period 3 as before, and now also a never treated or treated in period 4 unit. And so the alternative estimators will, for example, try to estimate, for this observation in A in period 2, they will compare the evolution of the outcome between 1 and 2 for A relative to B and C, right? That would be their natural comparison groups. And similarly, for A in period 3, they would again compare period 3 minus period 1 relative to unit C in 3 minus 1, right? The only one which is also observed untreated in those periods. So that's all good. But now look at period B, at unit B in period 3. The alternative estimators will only use the evolution of the outcomes of this unit between 2 and 3 relative to C, and not what happened relative to period 1. At this point, you're not using it for period, you're not using period 1 for unit B, but you are using it you're not using period 1 for unit B, but you are using it for period A relative to the same, unit C in those periods. And so there is no clear, no at all weaker assumption that you're imposing here by not using that extra information, which our imputation estimator uses all of, efficiently under homoskedasticity, not efficiently under heteroskedasticity, but still we use more data to impute the potential outcomes. So that's where efficiency gains are coming from. And let me actually show you right away the simulations. So we show that in the simulations, I'll skip the exact design, that the efficiency gains are realized not only under homoskedasticity, but also under heteroskedasticity, under autocorrelation of residuals. In all of these cases, the efficiency gains of about 15 to 40% are realized. And in addition, something which we again didn't know until we did the simulation, it's not true that by using more information, we're more sensitive to violation of parallel trends like anticipation effects. That's also not the case. I'll skip the details. Okay, so to kind of add up, to sum up what we add here, there are several advantages of our imputation approach besides efficiency. So it transparently maps your model of untreated potential outcomes to the estimator. And because of that, it will extend immediately to settings beyond event studies. I'll show you in a minute. By separating testing and estimation, we like it conceptually, but also turns out we mitigate this bias that John Ross has pointed out of conditioning on pre-trained test passing. We don't require random sampling, unlike other papers, and so that allows you to specify any weighted sum of treatment effects as your estimate, not just those based on cuts. So you can compare different subgroups of the same cohort to each other. All of this is fine. And then we have these analytically derived and computationally efficient standard errors, which in fact could potentially be used for other estimators as well, although we haven't checked. All right. So I already said that there are other imputation-based approaches. I'll skip that. Do you have 5 more minutes for some extensions? Okay, so I'll do that, and then I'll answer any questions that remain. So basically, because the imputation approach is so simple, right? You just estimate the model of potential outcomes on the untreated sample, and then you extrapolate it. It extends to many different settings that researchers have used. Repeated cross sections. So instead of having a panel, you observe different samples, random samples from the same population in each year. Not random sample nationally, but for example, you have a bunch of regions, and then in this region in each year, you have a different sample of people. So how to apply our method? Well, very straightforwardly, you specify your potential outcome, Y0, as the fixed effect of the group of the region. You can't put fixed effects of individuals because you only observe the individual ones. You put the fixed effect of the group, period effect, you do imputation just the same way. It doesn't have to be a panel over time. It can be a pseudo panel, like in some work, for example, looking at a cross section of different regions in different age groups, where your policy, a person is eligible if they're above, their age is above some threshold, and the threshold differs across different regions. Just an equivalent structure applies, so that's fine. Triple differences. You just specify a different model of Y0, which now has this bilateral fixed effects of like region and age group, region and period, age group and period, and then you impute the rest. In fact, if you are willing to impose a model of Y0 on anything, imputation approach works. We think that in different type studies, that's most kind of natural because there is a separation of Y0 from Y1. There was like no treatment, no treatment, no treatment, and treatment forever. So that's kind of a very stark case where imposing assumption of Y0 could be more plausible, while imposing assumption of Y1 less, so you want to allow for heterogeneity of the effects of your policy. So that tells you don't need to have standard panel data. You also don't quite need to have the standards, staggered timing of treatment, although not as much. So for example, we have something to say to the plain vanilla different diffs with simultaneous treatment. right? So, a treatment group is treated in period 5, everybody else is never treated. So that's a less problematic case to begin with. OLS has no negative weighting problems, no under-identification, and so on. But our points about separating testing from estimation still apply, right? If you run your your event study specification in this case with leads and lags, you're still generating the same problems, that you're losing power by not imposing parallel trends. And in addition, you are creating this Ross problem of pre-testing bias. So again, we say, well, do the same thing, do imputation, which in this simple case is just you estimate, you impose parallel trends, you don't include any leads first, you estimate the effects, and then you separately test for pre-trends by looking only at the pre-periods. Okay. And also, if you have this standard simultaneous timing case, but you have some controls or even unit-specific trends, now you're back to the same problems with staggered adoption. So OLS has negative weights and all of that, and yet imputation estimation would work just fine. I'll skip the rest. Treatment switching on and off is a little bit of a subtle issue, and I'm happy to answer questions about that afterwards. So let me just conclude that in this paper, we provide a framework to kind of understand the issues with conventional practice, clearly delineate different assumptions, and organize the solutions. So we related the problems with common practice to the conflation of the assumptions and the estimand, while when you don't conflate them, you get very naturally the imputation estimator and more generally our efficient estimator, even if some restrictions on treatment effects are reasonable. We proved large sample theory for it, got you conservative inference, implemented our Stata packages, propose a new approach to testing. The main thing is to separate it from estimation, really, and think about it differently. And then I talked about extensions a little bit. Our 2 Stata packages are now on SSC, so you're most welcome to download and let me know if there are any problems. Thanks a lot. I'll stop here.
Thanks very much, Kirill. So any questions that anybody has, floor is open.
Can I start with a question? Thank you, Kirill. This is great, interesting. So I had a question on how to estimate the weights, given that you had the unrestricted version. So I was just thinking, based on Chez Martin and Deutfor's way of estimating weights, which is regressing, your treatment assignment to your and getting the residual, and those weights are created out of those residuals. So I was just wondering, would that I guess I can apply that approach here too, right?
Well, that's the weights for OLS, right? That's the weights at OLS estimation. Right. That kind of, these weights give you the estimand of OLS, the troubled one.
Right.
I mean, those are certainly interesting. And if you're considering to use OLS for whatever reason, because you're not convinced by the current literature to not use it, then you would probably estimate them as Chez Martin and Hatfui show you to do, and you would at least know what you're getting. Okay. Here we're saying, no. We don't want the weights which are, determined by Gauss and Markov. We want weights which we want, right? We want the estimand, we want the average treatment effect 5 periods after treatment happens. You don't need to estimate the weights. The weights are immediately given. It's 1 over the number of observations like that you have. Done. In fact, the command will compute this 1 over for you if you tell it to estimate it 5 periods after. So weights here are not to be estimated. They are the starting point. And again, if you say, oh, I want to compare 2 subgroups, males and females, I can tell you the weights. It's 1 over the number of males times the diameter of a male minus 1 over the number of females times the diameter of female. That's the weights which corresponds to the estimand, which is the average males minus the average female. and so on.
Right. So the assumption behind that is you're putting equal weights to each treatment effect then.
Nope. So I gave you equal. Now I can, any weights WIT, a fair game. You choose them, you give them to the command, for example, and we'll estimate the corresponding average. Again, that's an interesting kind of thing which was surprising to us about the imputation procedure. So remember the 3 steps, right? Let me show you again. Here. Estimate alpha I beta t, impute tau's average.
Right.
Interestingly, whatever estimand you have in mind, the first 2 steps would be exactly the same. So after step 2, you've got your estimates of tau hat of the individual effects for each observation. In fact, in some sense, you can start thinking about the estimand only in step 3, what averages to take. You can take different ones. And any such average will be the most efficient one under, if you take the average of these tau hats, you will get the most efficient estimator for the corresponding estimand under Chomsky elasticity, regardless of what the estimand is.
So then just building on that, so if I, like, for example, working with CPS data or some PSID, if you're working with sampling weights, so the sampling weights would just be multiplied with this WIT.
Good question. So the sampling weights are slightly more interesting. Well, I guess the sampling weights, yes, you would just multiply the WIT, but the frequency weights are different. So if you have like observations which are really averages of some groups, right? You collapsed it by like region and year. And so what this means is that you don't have Chomsky elasticity. You now have lower variance of epsilon for the units where the frequency weight is higher. Then you would want to account for that and do the first step, estimating by weighted least squares. Right, and so the frequency weights play 2 roles. First, we use them to use most efficient estimator on estimation under heterosked elasticity of this particular sort. So weighted least squares in step 1. And of course, you also want to apply them for the estimand. And that's again what the command does. Okay. So there is a gap, there is a difference between the weights which apply to the estimand and define the estimand, and the weights which apply both to the estimand and to estimation for higher efficiency.
Okay, cool, good. I need to think more about that, but thank you so much.
Any other questions? Mm-hmm.
Kirill, I had one question. In the imputation phase, can you also use controls, like a vector of x's in the imputation as well?
I should really have said this. It's kind of slipped out between the main case and the extensions, because absolutely, in the first step of estimating, you can have any kinds of controls here or unit-specific trends or anything here. You, of course, then extrapolate appropriately, and then you take averages. So it works just fine. The controls are linear controls, right? So
right.
Callaway and Santana's paper is careful about like this flexible controlling and so on. For us, it's a regression-based approach. So it's a set of linear controls, just fine. Again, gives you efficiency under Chomsky elasticity of the residuals after those controls have been taken out.
Okay. And just to follow up, I'm having a little bit of a problem grasping the intuition of how you can impute a y or an I that's treated when you're using the untreated units.
No, you're not using untreated units. You're using untreated observations. That's something I mentioned at the beginning and should have repeated here, right? So you you can only do it because for this unit you have untreated observations before, and a unit which is treated for the entire period that is observed in your sample is totally not useful here because the imputation stage will fail. Thanks.
Okay.
Great clarification questions.
I just have a question about multiple treatments and treatments that turn on and off.
Mm-hmm.
In the extensions, you jumped over those ones to get to the question period. So you say that you can do some treatments that turn on and off, but you need to make additional assumption about spillovers.
That's exactly right.
Which makes sense.
Yeah.
And then when it comes to multiple treatments, it's more like thinking about, the way I understand it is more about thinking, is this really multiple treatment, or is there enough gap between things that we can actually consider more of a treatment switching on and off, whereas a unique treatment? Is that the case, that there's no real way when their units are, or when the frequency of treatment is so close together that you just can't identify the separate effects of the different instances of treatment?
That's exactly right. And I think it's what the literature will do soon, to think about like, okay, we can't separately identify them under no restrictions. What kind of restrictions are most useful in practice, in applications to get to make progress? I mean, ultimately, we want to estimate the effects of different policies, even if that requires more assumptions, right? You know, we still want to get useful predictions about, not predictions, causal estimates. So yeah.
Awesome, thank you.
Hi, can I just go back to the question about, I suppose in the previous extension, the triple difference, and the question earlier about what you do in the case when the treatment is not binary, but it's actually a continuous treatment.
So those are two different questions, right?
Yes, so those are two different questions.
So what about triple diffs? That's easy. It should say epsilon IGT actually for triple diffs.
Okay, yeah.
Yeah, so instead of running the regression of like y on the bilateral fixed effects and then d times tau, you just specify, you separate the d out, right? You look at the non-treated observations, you estimate this complicated bilateral fixed effect model on them, and then you impute. It works just fine. So that's easy. Any questions here?
Oh, no, this is fine. And then on, yeah.
So for continuous treatment intensity, imputation doesn't work and can't work. The reason is that there is no y zeros, right? If you observe all units treated to some extent, right? And you don't really want to impose strong assumptions on homogeneity, well, then you don't have any reference group.
Right. Yes, I guess the way out there would be to do this above median, below median, and consider the below median as basically to convert that into a binary treatment and then do what you're suggesting.
So I think in practice, that would be a simple natural first step.
Yeah.
Conceptually, it's a conceptual problem in here, right? That you don't have y zeros. So what do? You need to impose restrictions. This binary thing is a restriction, right? Which is kind of is practical and easy and nice, but ad hoc. And so that's again something which I think the literature and we hope to do some on that, but that hasn't been really done.
Great, thanks so much.
Thanks for the question.
I have one question if there is time. I was just wondering, like, when you're doing this never treated units, and there's something that, I don't know, like Imbens is also recently talking about using local surroundings around your never treated. Sorry? No, I was thinking about when you're doing a never treated, like if someone is sitting in California and then compared to people that are like California, but not someone like all across the US, right? So like, for example, California, New York, and maybe some other blue states, rather than comparing everyone. Would that work? Could I adapt it like that when I'm taking out Y0?
Yeah, so in some way. So you can specify, for example, within the model of Y0 here, you would add the interaction of years with like blue versus red state.
Oh, okay.
Now you will comparing only blue states to each other and red states to each other. Now, if you want to do something closer to matching based, nearest neighbor matching based on some continuous variables, I mean, that's an internal kind of, discussion of matching versus regression adjustments. And I don't have anything to say about that now. I'm actually curious if there is an equivalence there. I don't know. But with this kind of binary, absolutely, yeah. Just throw into the model of Y0 interactions with your groups and you're good.
Cool, thank you.
Anything else? Yeah.
Oh, I was going to say, if there aren't any more questions, then I just want to thank Kirill very much for being here and for this great presentation. It's been awesome.
Thank you very much, Taylor, for the invite, and for everyone for the lively discussion. Really nice to have lots of questions and so on. So I'm always available, if you have any questions about the paper or the command.
Awesome. And I'm going to do, I have a quick and dirty kind of basic example with the data code, if anyone wants to stick around for that. But if not, I'm hoping to record these onto, and then post them onto YouTube for later. So yeah, if no time for that, don't worry, you will be able to get it at some point. Thanks again, Anthony.
Okay.